And in this sequence, you can also see I've calculated when the first various numbers occur. For example, the threes are threes are easy. It's just wherever there's a 2 in base 3, and that's easy. That's already a sequence in OEIS. And but then the question is, well, how many are there for, like, how many 4s, how many 5s, and are there any 12s? Well, there's not any 9s, because anything that has a 2 in base 9 would also have a 2 in base 3. And in a generalization of that, there's not any powers of anything except for 2 to prime powers, because you can't have 2.
You mean in a counterexample?
No, this is just, I'm generalizing now.
The 9s don't appear?
There's no numbers for which the first time you get a 2 is in base 9. Because if you get a 2 in base 9, then you got a 2 in base 3.
Base 9 is not bringing anything new to the party.
Base 9 is not bringing anything new to the party. Nor is base any power of anything unless it's 2 to a prime power. Because you're not allowed to start, there's never going to be a 2 in base 2, so 4 is interesting, and 8 is interesting, but 16 is not interesting because 4 was interesting. But you might be asking, are there other 11s? Well, yes. The next number, like 31, is 58,130,496, and I think I found 2 or so more other 11s.
What's the property of that it shares with 31?
If you write this number in every base from 3 through 10, there's no 2s.
Okay.
Well, so that the sequence that says when the first 2 shows up, is that typically the small number?
I mean, it's typically 3.
Okay.
It's almost always 3.
That's fair.
But there are a lot of places where it is not 3. And the question is, are there finitely many 5s in this sequence?
So you tested everything up to that number?
No. I mean, it's an easy algorithm that can rule out certain numbers. It's like, oh, I got a 2 here, but this 2 is in like the 3 to the 9 position. So that 2 is going to persist for a while, so these next terms are all 3. It's easy to do that. So that's how you check up to like 3,000.
What was the term there? I can't read the invisible chalk that you're using here. What's the number you found, the big number?
This number?
Yeah.
58,130,496. There's no 2s in bases 3 through 10. And there is a 2 in base 11. And then there's no 2s in base 12 or 13, but you already had 1 in base 11. So then, of course, you can generalize this question and ask about other digits. You can ask about sets of digits appearing. You can ask about consecutive digits appearing. So another question that Neil and I have been thinking about a little bit for the last week or two is numbers such that the first time you get 2 4s in a representation is when the representation is 4 4. So this is sequence 2 6 8 5 4 0. So this is going to be numbers. This isn't quite what the sequence entry says, but this is numbers where the first time the base B representation has at least 2 4s is when it's 44. And there's a decent number of these up through 10,000, including some numbers very close to 10,000. But of course, representations like in base 3 of these numbers don't have that many digits. Or I guess base 5 is the first one that's relevant here. So there's not that many digits in these numbers. But these numbers are pretty common even up to that level. The question is, do these numbers stay common? Do they suddenly stop happening? We've only checked up to 10,000, so we could use some more data on it. And just I feel like these questions are likely to be kind of hard because just along these same lines, there's a conjecture of Erdős. Which says that 2 to the n has a 2 in base 3, and this is for all n greater than 8. Or it might be, I don't remember if it's n greater than 3 or n greater than 8, but I'm going to write n greater than 8 because if it's n greater than 3, then it's still true for n greater than 8. And then there's the conjecture of Sloane, where the same thing is true for 0 for all n greater than 15. This one I know is 15, because there's no zeros in 2 to the 15 in base 3. And these have been checked pretty high, and no counterexamples have been found yet. But these feel like they're in the same flavor as these types of questions. But just more insight or data on some of these questions. And just playing around with this, there are some interesting patterns that occur. So I don't really have
You can mention the magic word.
Fourier transform?
Fourier.
Yes. This all was spawned by a Saturday morning breakfast cereal comic where they talk about the Fourier transform of n as opposed to the Fourier transform, which is writing a number in a base where it has the most 4s, which spawns this, and then it caused me to think about this question. Or I decided 2 is a little more general than 4. All right, that's what I've got.
That's like Nathan. Okay, next up is Pat Devlin.
So, here's the question I was thinking about, and it's loosely associated to 2 of the other things that were already said, so I feel a little bit more justified bringing it up. But if you have, say, a permutation, which I like Nathaniel's definition, just there you have it. But I'm going to use a different example. My favorite 7-digit permutation is 8675309. And I'll write 10 instead of 0. 309, and let's just kind of pad it out to get some more. What am I missing? 1, 2, 4. If I wanted it consecutive. Cool, great. And you got your permutation, which, if you want to think about it algebraically, this is shorthand for the permutation where 1 maps to 8, 2 maps to 6, 3 maps to 7, and so on. This sort of one-line notation, not a cycle, but just there it is. And then you can say, hey, well, I got a permutation, sigma, just focus on the bottom line there. And you can say, hey, what's the longest increasing subsequence of sigma? And in this one, hey, what's the longest increasing subsequence? What I mean is you look at, for instance, let's get a good one. Not a good example. They're all short. Is it 2? I think it's 3. 3. There's a couple places. For example, this number, and it doesn't have to be consecutive, I don't care. This number. Hey, great. You got 3 in a row there, or some other stuff. And that shows that it's at least 3, and if you stare at it for a while or something, you can probably say it's 3. Is it 3 or 4? Or 5? Is it 3? Oh, we're going to go 3. So it doesn't have to be consecutive, but it does have to be sort of, in order. 6, and then a 7, and then eventually an 8, or 10, or whatever. Cool, great. Then you can skip some numbers in between. So you get 3, which begs the question, cool, now we have a thing where you plug in permutations and integers pop out. You can ask questions about that. Like, let's generalize a hair, because if you just you plug in permutations and then stuff pops out, it's not that interesting. If you only look at a single permutation, there's stuff to say. But let's instead say we have a whole set S as a set of permutations. All right, and I don't care how big it is. It could have 1 element. It could have a ton of elements. But maybe they're all permutations of n. They all have the same length or whatever. And we could define something like the average, the longest increasing subsequence, which is, well, the average. Yeah, just the average of this longest increasing subsequence. And now you have something that you map from sets of permutations to, well, not integers anymore, but it's not too critical. And let's ask a couple questions about it. Here's one question. How big can this function be? As you plug in different sets, what's a set or something that might make this average really big?
Instead of increasing of identity permutation.
That sounds like an interesting set to think about anyway. The identity, which if you write it out is like 1, 2, 3, up to n. And that's the only permutation in there. Okay. Well, yeah, then what does that do? How big is that average thingy for this guy? How big is it? Well, there's only the one thing, so it's just the average of the one guy, and it gets all the way up to n. So yeah, that's pretty good. And you couldn't possibly do better because
Great. And here's another question. Let's say we wanted to make it small. We want to make this average tiny. What's something else we could do?
N to 1.
I saw in a few places. We could do the same thing, but backwards. Yeah. So our permutation is still just one permutation in there. And maybe just write them in decreasing order. You can't get any, there's the longest increasing subsequence is only length 1, and well, you have one of them. You couldn't do worse. So you kind of understand the extremes, so that's not particularly interesting. But instead, you want to somehow make the question interesting, relating to Sloane's talk, something called Oolong's problem. If S equals the entire symmetric group, then what's this thing? What's the average over all permutations? And you say, oh, what's the average? Turns out, fun fact, it's about square root of n, a little bit more. So that's on average. It's square root of n. If you were to average
It was
over
done by the former, because the late Larry said also former by that. He did.
there you go, another connection to good old records.
And by that.
A question you could ask, which is the question that I'm going to ask, is what else can we say about this average of this longest increasing subsequence business if we impose some sort of algebraic structure on S? For example, let's say if S is a subgroup of our symmetric group, then what can we say about this average longest increasing subsequence business? And I'll phrase it in this particular question. Is it bigger than, there's going to be a question mark because here's the question, square root of n. I don't know. I'm not sure. I think so. I haven't really checked. This would be a good thing to check. Then you'd have to somehow just kind of putz around, and if you were looking at this question, you have to kind of say, oh, let's grab a couple subgroups of my permutation group and then calculate this thing. Calculating is not very hard, but there are a lot of subgroups would be the hard part or whatever. And also, I just haven't, well, I don't want to do it. Or you could ask some other questions if you maybe impose some other structure to maybe give you a hint that this is at least plausible. This is like a half question. What if S is a conjugacy class? Then it turns out, yeah, the average thingy is in fact bigger than square root n. So the phenomenon that we're sort of observing is that if you look at the whole group, you get like square root of n. And if you look at something algebraic like a subgroup, you probably can't do much better than square root of n anyway. This fact that the entire group gives you square root of n-ish is probably indicative that anything that's sufficiently algebraic is going to give you at least this big. You could, of course, do bigger by taking this subgroup, which gives you a really big average. So a big average it's not impressive if you just take the identity subgroup. But I suspect that any old subgroup is going to give you a big thing because I was able to show that any conjugacy class, the average is big. And that's got to mean something. Although in the symmetric group, these are less related than maybe for groups with normal subgroups. Anyway, that's all I got on that.
Let's thank Pat.
Have people looked at it? Is there any literature on this?
Someone asked the question and conjectured yes to the question on the far right.
My next tool would be Young Tableau.
Yeah, but then you have to somehow say, how do Young Tableau are great for longest increasing subsequence, but they're bad for algebra. But that's because longest increasing subsequence is probably bad for algebra, which you could somehow formulate as a statement like that on the right or something. But I don't know how to get in. But I'm trying.
Did you see the average for this very small one, for the smallest one?
What?
The average for the cyclic group generated by n minus 1 minus 2.
If you take that reverse thingy and then you
Generate cyclic group.
so that's going to be an involution. So that's going to be that. But yeah, if you replace subgroup with cyclic subgroup, I'd also be interested. Or doubly transitive subgroup, I'd be interested. You think cyclic subgroup's linear? Because I think so too.
Yeah, because there's no logic just cyclic subgroup of Sn. What is it?
You could get order n.
Yes, but then it would be linear because it has to contain the identity element, which is n.
Ah, but that only contributes 1.
How do you get the
It's
LCN?
in the average.
Okay, this might be a good place to wrap up. We can continue the discussion in private, but thank you all for coming to our open problem session. Let's have one more round of applause for all the speakers.